all the quirkiness of it.
Yeah.
All right, so making more neural connections with any kind of sensory input is very important. So, so we've talked about these examples: sensory desensitization, stimulating the skin gently, then gradually increasing coarseness, or how it's stimulated vestibular disorders, working on dizziness and or nausea that might accompany it, repeatedly performing graduated performance of those actions, and then hopefully that we habituate to that so that it is less disturbing. So habituation and sensitization, the book doesn't really talk about sensitization specifically on its own, but what we really are talking about with learning and memory is somewhat of the same idea as sensitization, because we are trying to get an excitatory response with learning and memory. So learning and memory is, and in your notes you'll see it has, it says long-term potentiation, and that is the technical term for learning and memory, is long-term potentiation. You'll see that used in textbooks, literature, etc. It involves persistent long-term changes in strength of synapses. So if we are habituating and sensitizing to certain input, we're trying to let go of those things that aren't important and latch onto those things that are important. We are working toward learning and memory. So it's, but the biggest, the most important piece to this is that it's persistent and long-term, and it strengthens those synapses. And in doing so, with the repetition of a task, it requires that we actually have changes at the cellular level. And so we're looking actually at the cellular level of learning when we look at long-term potentiation. And I'll show you, we'll look at exactly what this means. Requires synthesis of new proteins, requires growth, that's a correct term, growth of new synaptic connections, and modification of existing synapses. So we're not only connecting more, we're growing more areas to connect. We're not only growing more connections, we're growing more areas to connect. And so, hang on just a sec, yep. And so with long-term potentiation, we are actually taking, there are synapses that are there but not, they're potential synapses. And so we can fire them up, get them excited, basically, get an excitatory response there. Or we can just let them go, and any kind of synapse that you've created, any kind of learning or memory you've had before that goes away, that just hasn't been practiced, right? We've talked about this. Repeat to remember, and remember to repeat. That's how you keep your synapses strong. Same with anything, any musical instrument. If once you ride a bike, they say you never forget how to ride a bike, but you might have to dust off those synapses a little bit of an activity that maybe you haven't done for a while. So this is just showing you, and I'm not concerned that you have all the technical terms here. We will be talking about glutamate, but glutamate is an excitatory neuromodulator, neurotransmitter that will be a huge part of long-term potentiation. And it's saying that long-term potentiation begins with transformation, meaning that we're taking a silent synapse, and with enough excitation, with enough stimulus, excitatory stimulus, it actually starts moving these receptors that were not active, these inactive receptors, and they start kind of mobilizing themselves and getting to a place where they can actually become a receptor. So this is the cellular level of learning. So let's take a look here at long-term potentiation.
There are two explanations for what actually occurs at the molecular level during LTP. One hypothesis suggests that the presynaptic neuron fires at a normal rate, releasing an elevated amount of neurotransmitters.
How could that happen?
With an excitatory axoaxonic connection at the presynaptic.
And what might stimulate, what ion is stimulated to make that?
Calcium.
There you go. I forgot to let you.
It was going to be really sidetracked. I'll ask you later.
That's fantastic. All right. Moving on.
Release more neurotransmitter, you're going to get a bigger response in the postsynaptic neuron. The other way is actually to, for example, modify the receptor function so the receptors are more sensitive to the neurotransmitter.
In the second model, a normal amount of neurotransmitter is released, but the increased sensitivity of the receptor causes the postsynaptic neuron to fire at an elevated rate.
Which is probably both of those are happening. Both of those are happening. But just kind of a visual of what we just saw in action versus just on a picture. So.
What does the blue neurotomy do again? It's a neuromodulator.
It's an excitatory neuromodulator in learning and memory. It's going to be it's present in those excitatory.
Is there a vitamin you can take for that?
So can I just take my glutamate today?
Yeah.
So it's one of those things though, if you have too much of it or too little of it, it doesn't quite work. And so having just the right amount, just like anything. So yep, yeah, exactly. All right, so this is showing long-term potentiation, and like we mentioned earlier, it converts those silent synapses into active synapses, and then you grow these new receptor areas. And so here's an example of long-term potentiation begins the transformations we saw before. We get an excitatory response, glutamate, and so this is saying at 10 minutes, and I believe, I'm just going to pop this up for a second. This is A and B, so we're seeing this is A, B, C, D, E. So this is all in succession. All right, and so then we see that after we get a change, we're actually increasing our ability to have surface area for connection, and that's going to expand as well. You can actually become more sensitive along the postsynaptic membrane, and then we continue to have connections. As the more excitatory it is, then you stimulate those excitatory responses. So we may have a lot of neurotransmitter at first, a lot of presynaptic facilitation, and then just with a normal amount of neurotransmitter, we've got all these receptors now that are available. And so it's saying, yeah, this is a really important connection, and I want to keep this connection. And so it builds, that's how we build, that's what we do in physical therapy. We're building connections in so many different ways, whether it's a part of motor learning where we're trying to organize a person post-stroke or post-head injury where they don't have that motor learning component, and then actually doing that activity. So we're doing so much at this level. It's really, really exciting.
Is this why they do a lot of like pre-physical therapy for surgeries, like joint replacements?
Yes, and I mean, you want to go in as strong. There's certainly part of this. That is more about you want to go in as strong and as educated as possible because you're going to be sore and painful for a long time. And so you want that neuromuscular connection to be really good. I waited 5 months until I had my ACL surgery, and I went in super strong. Some people wait a short period of time and you're still swollen and irritated, and your recovery is going to be different because of that. So it's a little different.
Okay.
Reason, yeah.
Do the receptors become active in the same stage that they start accepting neurotransmitters?
In the same what?
In the same stage. I mean, when they become active from the neurotransmitter or whatever, can they immediately start accepting the same?
Yeah. When they're here, they're ready to roll. As long as there's, which is amazing. Yeah. They're once they mobilize and they are, so that the first mobilization is just all the excitatory response, and then once they actually connect onto the membrane, they're ready. Now, another thing that goes on, another action that goes on is long-term depression, which you can imagine is going to be the opposite. And long-term depression is actually those mobile receptors are removed from the postsynaptic ring, making the postsynaptic less likely to polarize. So this may be part of the pruning process. Remember we talked about how when you first learn something, especially if it's a motor activity, we're all over the place. We're overusing our activity, our muscular activity, and then we fine tune it, or even a musical instrument. Those are two, I think, very good examples of how. I mean, you think about like playing the guitar or a violin, your whole body's kind of trying to get your fingers on the strings, and over time, it's just a very, very minimal amount of movement, very precise, but very much minimal. So, long-term depression can play a role in fine-tuning how we learn, how our learning and memory is very precise, like a freeway versus a country road, of getting to that information. At first, your brain's kind of going all over the place, going to the wine country, and then after a while, it's on the Autobahn. It's like, I got that information. All right, good. So,
You got that song stuck in my head.
which one?
Country Road.
Country road. Thanks, Molly. All right.
You said it.
I did, but I didn't mean to. It wasn't my intent. Look at that. So then, there's just another little piece here that.
Role of support.
I got, we did that one, right? Yeah.
Oh, wait.
No.
Yes, we did long.
Yes. Question mark?
Wait, habituation.
Yeah, yeah.
So we did that one. Is that the second one? Yeah, there's the first one. Number 2. There's number 3. There's number 3. Okay, that's right. If it's not gray, then it wasn't seen. So, long-term potentiation, kind of in a nutshell. Repetition of stimulus creates our excitatory, postsynaptic, protein synthesis, genetic alterations via calcium channels. So there's probably some neuromodulation going on in here, right? Because we're creating proteins, right? That neuromodulator second messenger system is like part of this activity, just to kind of pull that into function. Converts those silent synapses into active postsynaptic membranes that remodel, as you saw, new dendritic activity and new dendritic formation. Therefore, new synapsing and increased contact between astrocytes and neurons. What's so important about this? Astrocytes.
Astrocytes are moms.
Lots of mom care, right? We've got all sorts, and dads. Dads are great too. But we have more nourishment, more support, right? These are glial cells. Astrocytes are glial cells. We have more support, whether that is in supplying connection, neurologic connection, messaging, whether it's capillary support for nutrition, increased contact, and we need that in order for that to survive, really. So there's this down here. This one's a little bit more technical. Oh no, this is.
How do you learn?
This is good.
This is a tougher question than it seems. You might know that you learn by studying.